Hello, network students. Welcome to week 2 of quiz sections. So today we have with us Will Scott. Will is a graduate student at the University of Washington, and he is a former employee at Google. And he's an expert on all things to do with Google. So today we are going to talk about some tweaks and some optimization that Google does to the regular network protocol stack. And Will is going to tell us about that. So Will, why don't we start with why are these tweaks required? TCP is a 20-year-old protocol. So isn't TCP IP a solved problem?
Yeah, so let me prefix my answer by saying that I didn't work on Google's TCP stack, but rather worked on some of their actual products. But I mean, when you think about TCP, TCP is a very broad protocol that is responsible for most of the traffic that goes across the internet. But traffic that is going on inside of a data center is going to look very different from the traffic that goes between your home computer and that data center, right? The computers are much closer together in that packets are going to get to their destination much faster, like a matter of milliseconds, or 1 millisecond, something like that. And also that there's a lot of bandwidth between those, right? Data centers are going to have a gigabit connection between any two computers. It's going to be fast. That's like at minimum. And so one thing that you're going to see is that in TCP we've got this slow start mechanism, which sort of probes the connection, sees how much bandwidth is available, and that's something that you need on the internet because you don't know how much bandwidth you've got. But in a data center you've got much more of that guarantee of what your connection looks like, and so you can set your parameters so that you largely skip that, right? You start with a large window to send so that for most of your connections they're going to send before you need to wait for any of your acknowledgments to come back to you. And so that lets you be more efficient. And that happens because you have a better sense of what traffic you're going to be sending.
All right, so can you tell us about Anycast? What is Anycast and how does it work and how does it help us?
Sure. So Anycast is a way where you can have multiple hosts that all respond to the same IP address. So if you've got a piece of content or a service, like for instance Google, but you can think of any piece of content, and you want hosts around the world to be able to get to that content quickly. One of the problems that have with the model that we understand so far is that all of the hosts are going to have, all of the computers around the world are going to have to go to one place to get that content, right? The IP address identifies one machine. And that's sort of suboptimal in that you don't really want the computers in Europe to have to go to the US to get their content if you've got data centers in Europe. And so there's a trick that gets played, and it's called Anycast. And what Anycast allows computers and services to do is that they can advertise the same IP address from multiple places. So the BGP protocol, the Border Gateway Protocol, which I believe has been discussed in your lectures, talks about how an AS, an autonomous system, is going to advertise a block of IP addresses that it owns. And so Google can, from multiple places where it peers with other autonomous systems, it can advertise that it owns and has a route to the same block of IP addresses. And so when your host goes to send packets to that IP address, it'll follow the path to the closest Google data center, and so it will end up following that shorter path. And Anycast gets used in a lot of places. It gets used by the root DNS servers and by many sort of replicated, widely available services. It's a common trick that gets played to allow for this locality in global internet services.
Thank you, Will. So before we talk about geo-sensitive DNS and what Google does with it, can you give our students a very brief primer on what DNS is, because we haven't studied the application layer yet?
Sure. So DNS stands for the domain name system, and it's the internet system that lets you resolve a domain name to an IP address. So the google.com or the washington.edu or the coursera.org name that we type into our browser and get used in many applications, when you think about the internet packet and the IP header that you've learned, there's no place for that to fit, right? The destination is one of these IP addresses, like 128.208.4.252 or something like that. And so the DNS system is a set of servers. They form sort of a tree, and the thought is it's a way to resolve one of those names, like washington.edu, back to an IP address that you can route to.
So what does Google do differently from the DNS you just described.
Okay, so one thing that you'll notice with Google, if you look up their record, is that they tend to set the time to live field very short, like something like 5 minutes, or even 1 minute. And what that does is it tells sort of intermediate DNS servers that they shouldn't cache the result very long. That Google's IP addresses are very volatile, that they'll change quickly. Another thing you'll notice is that when you ask for Google, you'll get something like 10 IP addresses back, not just one, which gives your computer some additional freedom in load balancing. But I think the caching is sort of one of the interesting points. DNS ends up caching a lot. There's a lot of sort of intermediation between Google's DNS server and you. Your ISP, your local network tend to cache. And so Google isn't able to directly say, you should visit this IP address when you want to visit us. And that ends up making their traffic management issues tricky because there's these intermediate systems that they can't control in between the clients and them. Another thing that you see from them to try and prevent this is the use of CNAMEs to alias their domain names. And so what they'll do sometimes is that a domain that tends to have logged in users will actually be an alias for some longer, more personal domain. And what that does is it means that your client will sort of save that, and in the future it'll look up that specific domain, and that lets the DNS server route you to the data center that has your data, so that they don't have to move it around to a different data center if your traffic ends up there.
So it seems like the gist of these optimizations that we saw was that in today's internet, the content is more important than finding the content, is more important than finding the right host. So if suppose in a hypothetical scenario, if the internet were to be redesigned and built up from the bottom up today, what do you think would be different?
Yeah, that's a good question. And a lot of thought went into the internet, and we've come up with something that's really cool. I mean, I think one thing that we've noticed, right, is the internet was purposely designed with all of the functionality pushed out to the edges, and that's given us a set of properties. We have really good evolvability. We can evolve protocols without having to change the intermediate, the core routers, and we also get good properties of reliability and availability. But there's other things that end up not working as well in that model. Things like quality of service. So that's when, if you want to watch a video and you want to sort of set up that channel and say, I really want to make sure that the video keeps coming at the same rate the whole time and guarantee that. Or mobility, if you want to be able to move your laptop to different points in the network and have the connections not lose. The internet isn't set up to handle that very well right now. So I guess to answer your question, I think we're at a point in the internet now where maybe we have a better sense of what it's doing now and are happy with that. And so that means maybe we can start pushing some of the functionality back into the middle. I think we're seeing that already with middle boxes. We've got this proliferation of smart machines in the middle of the internet. I think in a ground up design, you'd probably see this as well. Also because we've got a lot of big company players, and that definitely makes their life easier if they have more intelligence there.
Thanks a lot. And thank you for listening to the quiz section, and goodbye.
Thanks.